Welcome to Surveying 1, Module 4, which we are covering Chapter 5 of the Kalani book, along with a little other additional information that I have provided. So the reading assignment is for sections 5.1 through 5.6, 5.8 and 5.9, 5.12 and 5.14. Do not bother yourself with 5.7, 5.10, 5.11, or 5.15, and I'll explain why as we go. Going through the textbook, as you are to have read by now, have a different, just have a basic explanation. 5.1, 5.2 is carrying and setting up a level, and that is good information to read and things that will be covered in the lab. It's part of the purpose for the lab. The illustration here, figure 5.1, auto level is all we're going to concern ourselves with. We're not going to talk about dumpy levels or older 4-screw levels. These are just 3 screw levels, and regardless of which one you really look at as being A, B, or C, you identify the instrument, and the same goes for total station. This is the leveling of any 3-screw tri-brack mounted surveying instrument that you might use, robots, etc. There's going to be 3 screws. You consider one plane or one line being like A to B, and the other is C to a line perpendicular to A and B. If you've got it leveled in those 2 directions, the instrument is leveled. So again, that's something that we'll cover in the lab, and I'll try to do the best we can for the all online lab people, fall semester 2025 being the last time that will be incorporated. So that's how we'll level the level. Pardon the pun. Section 5.3 talks about the duties of the rod person. So the rod person is obviously the person who's holding the level rod. Standard industry use is a Philadelphia rod graduated in feet, which we've touched on in the previous module. And understand that the instrument person will be looking through the level, will eliminate parallax error, as was covered in the last module. And they'll be looking at a person who's holding a level rod on top of a point, which we need to obtain an elevation for or from. If it's a published or known elevation, we will be obtaining the elevation from it. If it is a new point or a point that we're laying out or that we're trying to determine an elevation on, then we'll be trying to determine the elevation of it. So one person will be looking through the instrument along a horizontal line that's leveled, and then we'll be holding the rod hopefully plumb. And here you see a dashed rod image, and what that's indicating is the book calls it rolling the rod, I believe, or waving the rod. We always call it rocking the rod, like a rocking chair. A rocking chair rocks in one direction to and from you, and that's the way that a rod should be. The instrument person would observe the rod, and as that rod comes forward and backward, bent back to plumb, and then further away, and so forth, this horizontal line, you see, of the instrument, where it's most plumb is the lowest reading on the rod. Otherwise, you're reading up the rod or back up the rod. So you'll read a higher rod reading than true anywhere except at the plumb point. So the instrument operator should watch for, should carefully study as the rod rocks forward and backwards, and record the lowest elevation on the rod that was read during that session. That's if you're going to rock the rod. Sometimes it's not practical, or sometimes your rod people are not wanting to. Sometimes there may be things that surround the point, like trees, buildings, electrical wires, where you cannot rock the rod, in which case many crews will keep in a truck if they're doing differential leveling, which is rare in North Georgia. It's very common in the flat areas, but they'll have a rod level, and this is something that you'll keep in your pocket, pouch, work vest, and you can see it's got this this right angle right here that just slides up on the rod. If it's an oval rod, it still just hugs right up next to it, and you can use this bullseye bubble right here to get the rod level. So in differential leveling, what we're doing is we're trying to level and determine fairly precise differences in elevations from one point to the next. Now this illustration here, figure 5.4 from the textbook, is a pretty good one. It's pretty simple. It's one way. That's something we'll need to talk about in just a minute, but in simplicity here, what we're doing is we're starting here at benchmark BM mill, and that's a benchmark, a concrete disc or a brass or aluminum or bronze disc in a amount of concrete. Typically benchmarks vary a lot, and the instrument person is set up right here, and they read the rod with 1.33 on the rod reading. They turn around to TP1 and they read the rod at 8.37. And you move up here, they backsided with a 0.22 reading, four-sided TP2 with a 7.91 reading. This is a good place to stop and explain the mechanics of differential leveling and differential leveling notes. Notice that where this instrument is set up really does not matter exactly where it is. We want our distances to be pretty well balanced forward and backwards, both to eliminate instrumentational error or systematic error as much as possible in the realm of plane surveying, but we also, as our sights might get longer, then that will moot out the effects of curvature and refraction. If we're looking the same distance in both directions, the correction factors apply equally and therefore cancel each other out. So, but if you pick the level up and move it over 5 feet or 6 feet, you know, your rod readings will differ, but it doesn't really matter. So if you've done any type of surveying before and you're used to setting the instrument up over a point in the ground, a traverse nail, a hub, a monument, or whatever, that does not really apply to differential leveling nor to trig leveling. Now, sometimes we incorporate trig leveling into the three-dimensional aspect of traversing. If you understand those terms, just understand that's something different. When we're strictly doing leveling, strictly one-dimensional values, this is all we're doing. So where the instrument is set up does not matter. The other thing I want to stress is there will be a foresight on TP1 when we're coming from our first setup, and then we'll backside back on TP1. So we're observing this point twice. And the next slide covers notes, and that's where I will elaborate on that. But in this, it's the same rinse and repeat. You foresight a turning point, then you move up and you backside a turning point. And I used a similar 3 turning point, and TP just stands for turning point. I used a similar 3 TP loop between 2 benchmarks later in this lecture for illustrating 3-wire leveling and stadia. So here are the notes, and looking back on figure 5.4, which you may can do in your books, or with split screens you may can do it on your ebook. You know, his initial rod reading on BM mill, and this is standard notes. It's always station, foresight, station, backside, HI, foresight, and elevation. except that we kind of changed these up a little bit with 3-wire leveling, because most field books have 6 columns, and so we're going to use those 6 columns differently in 3-wire leveling. And 3-wire leveling is not actually done that much, but there's really no reason not to 3-wire almost anything, and you'll see why in a minute. You can eliminate errors, and I'll kind of illustrate that here. So again, looking back from our first setup, the back-sided BM mill with a 1.33. Now, we knew that the published elevation of benchmark mill was 2053.18. So we add 2053.18, which is the ground elevation. We're measuring 1.33 feet above that is our level line of sight. That gives us an HI of 2054.51. Now, this is where standard note keeping, and we're going to dwell on this slide for a minute because this is where you can really learn a lot about differential leveling. Even if you don't do a whole lot of it in your career, this is very important to know. So this format of notes, I call it kind of condensed. There's no blank lines. You have to have a full understanding of what you're doing to follow this. So here we know from the diagram and or from having actually gone out and done the surveying that the very next thing we did was not this 0.22, it was the 8.37 foresight on TP1. So our workflow is really going right to left and then left to right, because after we get this 8.37 rod reading on TP1 and we compute an elevation of 2046.14, then we move ahead, backsight this 2046.14 TP1. Here's our backsight reading of 0.22. Then 0.22 plus the computed elevation of 2046.14 gives us a new HI of 2046.36. Now, I really want you to take a minute after this lecture and go back to your book. It's on page 106 and 107, and I believe it's on the same screen on the ebook. And observe this, and follow the notes in page 107 and compare it to figure 5.4 on page 106. One reason I stress this, even if you're not going to be doing this a whole lot, it's very likely that at some point in time in your career as a surveyor or as a project engineer, because I know a lot of you are engineering students and a career in surveying is not what you're looking at, but this is the sort of thing that engineers and contractors do on construction projects all the time. And I see big dollar liability lawsuits creep up occasionally, and it's usually from not understanding something like this, whether if it's the surveyor, the general contractor, or the engineer. I've saw all in my nearly 40 years of folks going out and saying, oh, there's the benchmark, we've got to set this lift station at this elevation, or our first manhole needs to be at this elevation, or whatever that is. It's often, this is just adding and subtracting. There's no calculus, no trigonometry involved in leveling. It's just adding and subtracting. But it's easy, due to how it's all put together and been organized, to get confused. And so, pay attention to this. Make sure that you understand all the way through what's going on. So here, when they foresighted, now they've moved up, they've backsighted TP1. The workflow is kind of going like this, which is kind of complicated. That's why I propose and use the uncongested note method, which we'll cover in a couple of slides. According to the diagram, the foresight on TP2 was 8.91. And the reason of that probably is, and you'll see this in the lab or in the diagrams or both, if you're looking at 7.91, it's right there at the 8. Even though the 8 is above it, that 8 will predominate your thinking, and you'll record 8, and then you'll go down and read the 0.91, and that's what goes in the book. I've done it myself. It's very common. That's also why it's very important to be very diligent with your rod readings, and it's another reason why the 3-wire method gives you a really good check. What probably happened, and I've done this, you run the loop out and you've got a foot bust. Well, 9 times out of 10, that tells you that you've read a rod wrong. But you've got, just in this simple reading, you've got 1, 2, 3, 4, 5, 6, 7, 8 rod readings. Which one's busted? You don't know. You basically have to go start all over and run it, but you're not going to be setting the instrument up at the same height every time, so you can't detect where it is until you turn a backside and a foresight, subtract the difference in elevation, and figure out if you got the same difference in elevation the first time or not. It's one reason why the 3-wire method can really save you some time if you have a bust. So, if you don't have a bust, it's just a little extra time taken. Maybe it's insurance policy. But here, in theory, the authors of the book did this to illustrate, okay, you recorded an 891. Once we added up the foresights and the backsights, it was a foot different. I mean, actually, we're 300ths of an error of a foot here in error, but they're calling it a loop misclosure. We call it a loop closure or a loop error of 300ths of a foot. This is where they've added them up. And in standard note keeping, this is good. The backsights and the foresights should sum. The foresights are minus, the backsights are plus. They should sum. This means that there's 300ths difference, and so you've got 300ths of bust or 300ths of error of closure. But going back to in theory here, they ran this up. They found that this was 41.21. Well, that's a problem. We've probably got a foot somewhere. And maybe they realized this should have been 8.91. They went back and set up on somewhere around their second setup, backside of TP1, foresight of TP2, confirmed that the difference in elevation was around 7.91 minus 0.22 feet, and it was, and they called it good and just corrected this to 7.91 and carried on. So that's how that works. Now, take another look back at figure 5.4. If the BM in the oak is not a known elevation, then it's just another turning point, and you need to turn back through either these same 3 turning points or 3 new turning points and call them 4, 5, and 6, and close back in on your initial benchmark. And that's what we'll do in the lab, is we'll start and close at the same point. That makes it a little simpler, but in the real world, you're liable to do one as much as the other. Now, we're going to talk about, we're going to move on finally. We're still in section 5.4, but we're going to talk a little bit about stadia. In your math courses to this point, you've no doubt long ago studied the mathematical relationship of similar triangles. Stadia is a concept where similar triangles are employed in estimating distances or measuring distances. We're just measuring them a lot less accurately than we would with precise surveying measurements. Now, figure 5.6 and the formulas in the textbook, 5.1, 5.2, they go over the optics and the similar triangles. I'll simplify it like this. Within the auto level, we have a triangle, which is going from your eye to where it sees the top line, to where it sees the bottom line, to where it sees the middle line of the crosshair. And this little triangle inside the prism is directly proportional and similar to the same triangle that you're looking at through the eyepiece outside the instrument to the rod. And over the centuries, designers and manufacturers of levels and other instruments have become very crafty at how they do this. So here is what you're looking at through the eyepiece of the instrument. You've got the top line. Let me change colors back. You have the top line right here. You have the bottom line down here. And you have the middle line right here. These on the top and the bottom are the stadia lines. The one in the middle is the sight line. They all start with S. But the stadia line, which I've denoted with the T, that is this given interval in the eyepiece, the reticle, the crosshairs of the level. And these are set up in virtually all auto levels manufactured around the world with a 100x stadia interval. And that works for feet, meters, works for whatever units you want it to be. Because here we're reading the top. Here's the 12 again, a third of the way up. We're 12.38. And then here we're right below 12. Remember, I just talked about how you're liable to read this as being 12.98 because you're looking at a 12. This big red flashing 12 right here is going to influence your thinking that it's that it's 12. Just remember, you're below that. You're 11.98. The stadia interval here is 12.38 minus 11.98. Now they've got that right here, equals 0.40. Your stadia interval is or multiplier is 100, so you take 0.4, multiply it times 100 over here, and that means that the distance from the front of the level to the level rod is computed to be 40.00 feet. But that is a huge misnomer, right? Think about that. Our most significant digit is the 4 or the 1, because there's 2 decimals after. So this should not be 40.00 feet. This should just be 40 feet. Please be mindful of your significant digits. We're not measuring with stadia accurate to 0.00 of a foot to a hundredth. We're not. Stadia is good for 1 foot, and that's plus or minus a half a foot because we're still rounding. But it's interesting. You can take out a tape measure and measure from the level to the rod, and you're going to be all over 40 feet. So it's not a precise distance measurement technique, but you can keep track of where you are along the route of a level survey or a profile simply by taking a stadia interval. And that's again where the 3 wires can come into place. Now here, if you also look at the line of sight, we're reading 12.18, and all of that averages. If you take the reading of 12.38, 12.18, 11.98, add those up, divide them by 3, they average out to 12.18. If the average comes out more than 100th from your direct sight reading, you got a problem somewhere. One of those 3 readings is wrong, or you're doing a really bad job. So that's another thing, is right then and there before you move on, reading all 3 wires will let you know if something's going on. And sometimes it might be that you've misread the middle wire, which means if you weren't doing 3 wire, you'd have a level bust right there. If you misread one of your stadia wires, well, you wouldn't have done that if you were just reading it one time, but it's important to do this, and especially if you need to know the distance around. Now, we're going to talk a little bit now. Let's see, we're still in 5-4. We're moving to 5-5. I think we'll hold off on going into 5-5 for the moment. Yeah, we're going to stay right here and look at figure 5-7. And this is just a simple illustration of, right here is our curvature and refraction error on our backside. On our foresight, it's the same if our D1 and D2 are basically the same. They cancel each other out, which is nice. Moving on to 5.8, or figure 5.8, which goes into section 5.5, is the precision. So the distance, if you record a stadia distance, because in differential leveling, we're not carrying an EDM, we're not carrying a total station, we're carrying an auto level, because all we're doing is we're trying to focus on the Z value, the elevation. We're not looking at X and Y all that much. Distance is a function of the two-dimensional. And so what they've done here is the length of this leg between A and B is 1 mile, B and C is 0.7 mile, and they ran it back and you got 0.8 mile here and 0.5 mile here. You do a weighted average of dispersing the collective error, which they determined to be, I can't see it in my professor notes here, but that's looking like 0.12 or 1.18, 0.22. There's 22 hundredths of error in this level loop that looks to be about 3 miles. So this is how you would do it. It's weighted. So 8 hundredths is that portion of the 1 mile out of 3 that you're adding, and it's better to illustrate with a true example. So here are sample notes that I made. I just went on an imaginary road trip to Todd, Arizona, which is out in the middle of nowhere, and I invented some features out there like a railroad. There is a highway, 425. And these are my notes. This is how your level notes and any notes or data that you record should resemble. Okay? I'm not perfect. You can see this does not look exactly like your your lettering guide, but my 4s, my 9s, my 6s, my 8s, my 7s are all made correctly, my 2s. So here we start off, and you'll see that we don't cram everything we can on a page of paper. And when I started, everybody seemed to be a lot more frugal. It was not, the electronic data now is virtually free and limitless. Field books cost money. You didn't want to carry you didn't want to carry 2 field books. You didn't want to have a bunch of field books laying around. So that's why I believe the standard note format, which I talked about with the example a few slides ago, they crammed a lot in there. And as long as you were really on your game and you did this all the time, it made sense to you. I reject that, especially for differential leveling in this day and time, because very few people differential level frequently unless you're laying out foundations in Florida or storm drainage in Florida or South Georgia, or in parts of even downtown Atlanta where the elevations are very tight. I have saw that. So maybe I shouldn't be so dismissive, but even then we're not doing it very often. So this format keeps us in a chronological order top to bottom, just like reading a book. And that way we don't have to try to remember this slanted, what's going on. Okay, we're reading from over here, and then we come back over here. Now we take all that out. And this does apply to 3-wire. It would still be the same if you just took this wire in the middle. But here with the top wire was read at 1252, the middle wire at 776, the bottom wire at 298. Add those up, divide them by 3, and you get 7.753. Here's your check. That's within a hundredth of your line of sight wire reading. Now this has a published elevation of 202.52, which comes right over to here, as that is the elevation. Now notice I have added, the standard differential leveling note format is that this fifth column is going to be elevations, and the sixth column is going to be adjusted elevations. But in 3-wire especially, you're going to be carrying the distance, and so we're going to add a column for that, and we have plenty of space, especially with the non-compressed note format, where we can have the elevation over the adjusted elevation. And I said Arizona, sunny, 95 degrees. I didn't invent a crew, which would be listed on notes. That's my bad. Your field group should be added to your notes. Probably make maybe even a cover sheet. And notice I say early light. Why is that? You get heat waves. And heat waves will distort because you'll be looking, I've done this, and that's when you know it's time to quit. You'll be looking right here, and this is bouncing up and down. Well, the earth's not shaking and the instrument's not vibrating. That's heat waves. And you just can't do it. Some surveyors, especially in the really hot climates like Arizona or South Florida, I've known or heard of them to go out and do all their surveying at night just because there are no heat waves. Flashlights and headlights in the weather is a lot more tolerable. But even in Atlanta in the summertime, I've encountered heat waves that will distort you as close up as 300 or 400 feet. And that's sometimes by 9 or 10 in the morning, especially when it gets daylight a little after 6. You got 2 or 3 hours worth of sunlight coming in and hitting the asphalt and the ground, and it'll just start those heat waves. Another reason that's important is 3-wire leveling, even though you can use it on the shortest of sights, 3-wire leveling is usually done for longer range baselines or level loops where your sights are going to be farther. And it can be pretty hard to read a level when you're 1,000 feet away, to read a level rod. And the only way they do it is some auto levels have higher magnification. The more expensive the level, usually you're getting a bigger box, a bigger focal length, a bigger lens, and you can focus better. So if you're going to be doing 3-wire leveling, long range leveling, you're probably going to have a pretty expensive auto level that has higher magnification. They also make the brackets that slide up and down. You may have saw them in one of the illustrations in the book. I believe it was in the last module, where you're basically creating a bubble or a circle that you might not can see all that clearly when you're 1,000 feet away, but you can kind of tell when you're centered of that bubble. And either by hand signal or by walkie-talkie or cell phones, you might be talking to someone 1,000 feet away and tell them go up, back down, or right there. And then they have to radio the rod reading back to you based on where you told them to stop adjusting the creeper. So that's what you'd be doing here. This is 954 feet of stadia difference. If you take 12.52, subtract 2.98, that's the top wire minus the bottom wire, that's 9.54 times 100, 954 feet. So right there's where we get that. Now, our average here, our average backside readings for the three wires came out to 7.753, so our HI is 210.273. Now understand, all of this is basically estimated to the 100th of a foot. Now if you're up close, I will often estimate to the half of a 100th and go 0.525, 0.5195, or 0.515. But that's sometimes just when it's really close and you can't call it, because that may come back to you again. You can't call it another time, they cancel out, or there's nothing wrong with coming up with an estimated value that's a half a 100th. But then, so we've set up and we backsighted Todd, and now we're foresighting TP1. And we need a little description on. brass disc Todd-ARIZ at corner of Stone Pillar on the southwest corner of a water tower at a train station in Todd, Arizona. Published elevation 202.52. TP1 is a railroad spike set in a turn lane on the east side of Highway 425S, approximately 1/10 of a mile south of Garnett Road. So that may not make a whole lot of sense to anybody coming back a year from now or 5 years from now or even tomorrow if they weren't on the original crew, but at least you know where you were looking. And so then we take our three readings, 11.00, 5.78, 0.58. We average those, we get 5.787. So that's within 100th of our middle wire read, so we're not busted. We're just reading here. The stadia distance comes out to 10.42. And so our accumulated distance, which will come back to mean something in a minute, from Todd to TP1 is 1,996 feet. May not be a straight line distance. We don't care. We're only concerned with the distance along the level loop, which is from Todd to where the instrument was set up, which we don't know exactly where it's at, and it doesn't matter, to TP1. The distance of those, the sum of the two lines that we just talked about is 1,996 feet. That's our accumulated length into the loop at this point. Now, instead of being all complicated with the diagonal lines, now we're going to go set up somewhere else. And we're going to backside TP1, and we're going to do the same process. 1389, 968, 947, average out to 9.68, so we're all good there. We compute an HI, and then we have moved up. So then we're going to shoot TP2. And here we go with shooting TP2. We're computing the distance between our setup and TP1 on the back side, our distance between our second setup and TP2 on our foresight, using stadia intervals, and now we're at 3989 accumulated distance. And our computed elevation of TP2 is 207.439. Then we move up, we backside TP2, we basically rinse and repeat. And then we foresight TP3. And we're still just doing the same process. Then we'll move up and we'll backside TP3. And then we'll foresight BMR7. So we foresight BMR7. We come up, we do the same thing. We're averaging all three wires. This one's within a 0.5 of this one, etc., etc. The stadia distance gives us stadia interval gives us a stadia distance of 894. So our total accumulated feet is 7,397 feet. Our computed raw elevation on BMR7 is 203.002. Now, BMR7 is a U.S. C&GS monument 40 feet east of an old store building, 14 feet north of a gravel drive running to the east, 0.8 of a foot south of a witness post. Published elevation 203.04. So our vertical error is 38 thousandths. That's the difference between the published elevation and our computed elevation. Our total distance is 7,397 feet, which is 1.40 miles. We'll come back to the significance of this momentarily. There's any number of ways to use simple arithmetic to decide how you want to adjust. The easiest way for me is we're going to adjust 38 thousandths into 7,397 feet. That's going to be an adjustment of 0.000005137 feet per foot. So what does that mean? If you look up here, our accumulated distance, 5718 times 0.0000537 is 0.029. So our adjustment is 0.029. Now, we came in low, so we add, so that they eventually add up. If we come in high, we would subtract the adjustment. So what I did there, that pulls our initial 202.882 computed elevation, add 0.029 to it, we get an adjusted elevation below it of 202.911. Now let's just say that either one of those, we had published elevations in between. So this is why this was being done. Let's talk about that for a minute. There was a bench, we did our research, we looked at the quad maps, we called the Arizona DOT, we called the National Park Service, we called whoever, phoned a friend, a surveyor in the area, and we found out that there was benchmark Todd that was pretty good, and the benchmark R7 that's down there by this old store building. Well, about halfway in between, somewhere around TP2, they're going to be doing a new culvert on Highway 225. So I added this. I crammed it in this little space here on the right side. This is where your notes usually go. Usually all of you numeric data comes over here on the left side in the columns. You're going to have grid paper on the right hand side that's for sketches and for notes. And so what I did was I came in here and I made our sketch, our survey sketch in here. And any good sketch should say not to scale, unless you actually drew it to scale. There's times when you may take a pocket scale, something like this, and draw something to scale. Often if you're sketching up a big complicated building, it's a little easier to do it to scale because you don't wind up guessing at it and wind up coming out with your corners a half a page, same corner being half a page away from each other. But here we're saying no scale. The other thing that you got to have is a north arrow. You might have drew this the way where you're looking at it with north way back over your shoulder. So there you might say north this way. That's all right. As long as you know which way north is, then you're good. But here, Todd is up here by the railroad track. We set the instrument up. Let's use purple. We set the instrument up somewhere in here where I could see Todd and I could see TP1. And then I came set up over here the second time, somewhere I could see back on TP1 and I could see TP2. If you remember, TP2 is a chiseled X on a head wall. And I've added to the sketch here that it's a box culvert. And let's just say that the new culvert project is just right here next to it. They're going to tear out the old culvert, very last thing. They're going to use my TP2 elevation to build this new culvert and this new drainage system, and then they're tearing everything out. So during the course of construction, we might set another turning point, but we know from looking at the plans that TP2 is going to be there until nobody needs it, and we're going to be back out there a lot of times setting all kinds of elevations for this thing. And if not, we can rerun the level loop. It only took an hour or two with pickup trucks and so forth. But this was the whole goal, was to get an elevation for TP2 right here to be in the vicinity of this construction project. So we could have ran it back in on Todd, but we really thought it would be good to confirm the elevations between Todd and R7. Possibly somebody else in the future, say Todd's gone, they might run it in from R7. So you got to be thinking ahead and realize, well, we need to know that these two benchmarks G-haul with each other, and they do. So then, we came over with our third setup and we shot TP2 and TP3. Then we came over here somewhere and we connected TP3 with R7. So, that purple line is the level loop that we ran. And it's not a straight line between Todd and R7, but we know the accumulated distance along that purple line is 7,397 feet. With 8 stadia rod readings being plus or minus 8 feet, or being plus or minus a foot a piece, then I'd say that's 7,397 plus or minus 8 feet. That's good enough. That gets us to 38 hundredths of an error in 1.40 miles. So we're going to talk now. 5.5 in the book is still precision. Well, first we're going to talk about Georgia board rules. And Rule 180-7-.04, 1A and 1B talk about the required precision. Now, if a circuit levels between precise benchmarks or closed upon the initial benchmark, now this is for field run precision leveling. And that's where the project's probably really tight from start to finish. Example that I use is a sewer line that we ran in Dalton, Georgia a few years ago that was at like 0.04%. Well, we literally had like 0.2 of a foot of fall in a couple of thousand feet. It was very flat, and that's just where everything had to be. So every hundredth of a foot counted on this long sewer line. It was ridiculously flat, so every hundredth counted. So we took our auto level and we went and ran a complete level circuit, closed it back in. Thankfully, we were within, I think, 15 thousandths, 14 thousandths, a little over a hundredth of a foot, which was okay. We adjusted that out, even though it was, not a whole lot to adjust out. Hundredths count. But let's look at our example here. We just had 38 hundredths of a foot in 1.4 mile. Does it pass the test of Rule 1A here? So the way that all these precision requirements for levels are set up is error amount times the square root of the number of miles in the circuit. And that's how all of them are. We'll look at another standard in a moment. But in Georgia, we really just have two, which is A for precision leveling. So we got 1.4 miles. The square root of that is 1.18 times 0.02 means we were allowed 24 thousandths of error, and we had 38 thousandths of error. So our level loop in Arizona did not meet Georgia precision leveling standards. We would have to back up and do better. Maybe we should shorten our sights so that we're not estimating our rod readings so high. Lots of different things we could do. But this is really just to get a local benchmark on a construction project. And it's not tied to Todd or to R7. It's just out there on the highway. So if we're off 38 hundredths from Todd or from R7, or preferably, hopefully, like less than 2 hundredths, like less than half of that, since that was our total error from one benchmark to the other, then, we're in pretty good shape for building this new culvert. And by the way, when you go in from one benchmark to another, you're assuming that the published values are perfect. What if the published values are out 38 hundredths of a foot and our levels are perfect? Then we've added 38 hundredths of a foot of error into our observed elevations. That's just something for you to think about. Just trying to help you think big picture. So here though, for a local benchmark, 1/10 of a foot times the square root of a mile. So we're 1.4 square root of 1.4 is 1.18 times 0.1. We're allowed 12 hundredths. We're well below that, so we're good. Let's look at a little bit more broader picture. The Federal Geographic Data Committee used to have, when everything was done manually, before GPS and so much computer and digital technology came along and remote sensing, so that the USGS and NGS had their standards. FGDC kind of replaced all that in '98, but those old standards live on. And basically what you need to know is it was first order, second order, third order. You may see questions about this on the exam. Some of them still do linger. First order being the tightest, second order being really okay, and third order being kind of loose. And so there it was first order, you were allowed 0.017 per mile. Second order was 0.035 feet per mile times the square root, not per mile, 0.035 times the square root of the circuit length. And 5 hundredths for third order. So here 1.4 square root times 0.035. For second order work by national standard back in the day, we were allowed 41 thousandths, a little over 400, so we were just below that. So our Todd to R7 loop was a good second order level loop. Now, try not to be too long-winded. This has us in 5/6, which we just talked about adjusting. Notice figure 510 in your book, which I've taken out of the slides. It still uses the compressed note keeping method, and all those arrows and things that you have to watch their video and really study to understand that. To me, it's too complicated. We're going to see, we're skipping over 5/7, which is reciprocal leveling. Honestly, I've never heard of that before. I think that might apply out around the Mississippi River somewhere. If you're doing surveying out on the Mississippi River, go back and study reciprocal leveling. 5.8 is 3-wire leveling, which we've already covered ahead of time. Then we're coming back to 5.9, profile leveling. And I just talk, profile, this is the ground if you cut it cross section. This could be a straight line, or this could be an irregular line, just like our Arizona level loop. In between, you got, turning points, and then you've got these land features. So the whole purpose of this is to draw the profile of the land so that you can design a sewer line, a road alignment, whatever that may be. Now, what becomes tricky here is you have to either measure with a tape or with Stadia to see where along this line every rod reading was, so that you can compute it to stations. Like if your first instrument point, you can see right here, here's where the instrument is. You get a Stadia distance, he's probably 135 feet on his Stadia, so he has to take off the Stadia reading to this first shot to figure out how far he is, and nobody's going to do that anymore. That was from years ago. But if you were to, see, you take the Stadia and can get your distance over here. Well, you don't even, they're not showing how you get your distance. They're just saying, from the BM, and then you got 0 plus 0, 0 on the profile, here's your rod reading. So then here's your intermediate foresight on all these profile points. Anymore nowadays, we're drawing these profiles from LiDAR collected topography or field run total station collected topography. I don't know of anybody that still does profiles by hand with a auto level. This slide here is basically your stations and your elevations. Now they've gone ahead and drawn in a profile of a grade, which is either a sewer or a new street. They don't really say, but it's a negative 0.15, pretty flat profile, and that's the purpose of plotting this, or surveying this existing profile, is so that you can lay across this new profile. And any profile sheet, you're going to have the horizontal and the vertical scale. They're usually exaggerated, otherwise it's just a flat line for the most part. That gets us over into 5.10. We're at 5.10, we're talking about grids and cross sections for borrow pitting. And again, if you're doing a grid area, we're not going to be staking out points with a level and with a tape measure or an instrument and driving stakes in the ground to come back and shoot anymore. We're going to do this with an approximate grid paced off or staked out with a total station. So don't worry yourself too much about that. Then we want to look at with a hand level. We talked about that sufficiently the last module. Do read 5.12. I'm not going to expound on it, but these are all the different sources of errors that can creep into leveling. And it's important to understand this, even if you never revisit it. I may throw in a test question or two from it to make sure that you read it, but it's not quite as important as a lot of things. And 14 is just a little, or 5.14 basically is worth repeating, that errors and running levels are reduced but never eliminated by carefully adjusting and manipulating instruments and rods and establishing standard field methods and routines. So some following routines prevent the most large errors or quickly disclosed mistakes. Checking the bubble before and after each reading, just to make sure that your level has not gotten out of bubble. Maybe you set it up in some soft ground and it shifted. Maybe you kicked it and didn't realize it. Maybe an animal bumped the instrument and knocked it out of level. So if the instrument's not level, you're out of luck. You need to just scrap everything that you recorded unless you know exactly when it happened. And even then, you've got to re-backside and carry on. Number 2, using the rod level. Make sure you either use a rod level or that you rock the level. Keeping the horizontal lengths of the plus and minus sights, your foresights and back sights, equal, or as equal as you can to possible. Running lines forward and backwards. In other words, you're not just going to run a level loop from a benchmark out to your last turn point and say that's all I need. You got to run it back and check it in. Otherwise, you don't know if you've got a blunder or some kind of bust halfway in between, and you have no check to know how accurate that you are. Making the usual field book arithmetic checks, making sure that your back sights and your foresights add up. That's a simple cheat sheet way. And sometimes if you got a really long circuit where you might accumulate a lot of error, break it up into smaller ones. That's not something we're really going to be looking at doing that much. And that concludes Module 4, Chapter 5. There will be some standard level notes and things included in your lab instructions, and we'll pick up the discussion there, but this concludes the lecture section. Thank you.